another time. And we're going to talk about another kind of problem that we're going to work on called forecasting. And what forecasting is about is literally we're trying to predict some value over time. So if time is our independent variable and we're trying to predict something, say y, and say we have data points that create a pattern like that, we just want to predict what happens in the future, further on in time. Given the pattern we've seen, what values would we predict? Specifically, we're going to talk about a few algorithms that are only really useful for predicting short-term future events. We're not talking about predicting far out in the future, way out over here. We're just talking about predicting immediately in the near future what values would this function or this pattern yield. This is a very useful algorithm or a very useful approach to modeling for a lot of things, like when you want to predict stock prices. So you're trying to predict the stock market and whether or not you should buy a stock or not. You want to predict what value will the stock have sometime in the future. Okay? And a lot of monetary, a lot of currency, a lot of money type situations involve that same kind of a forecasting approach where you want to say, how does this thing change over time so that I can use that knowledge about what I think the future will look like to make a decision to buy something or not buy something, or to sell something or not, and so forth. So we're going to talk about specifically 4 algorithms, and really they're just 4 successively more complex algorithms that kind of build on some of the others for doing this kind of short-term forecasting. Okay? So we'll do a few examples inside of Excel, and I'll try to illustrate them here so we can kind of keep a record of them. The first thing you can do, basically the most simple thing you can do, is you can say take an average of the values over time and use that to predict the future. So over time, you're going to take an average, moving average model, or moving average algorithm. So over time, you're just going to take an average, and as you find more data, you'll add that onto the average, and so in that way, the average kind of moves along. So for instance, if I had data values here, here, and here, so I would take the average of those 3 values, say something along there, and predict that as the future value. Okay? Now maybe the real value would have been something like this, and so I obviously was wrong in my prediction. I predicted something that was the average of the first 3, when in fact the next one was up a little higher. So for the next time period, what I want to predict is the average of the 3 previous values to it. So I'm going to leave off the first value and now just take the average of the next 3 values. So this one, this one, and this one, and use that to predict the next point in the future. Okay? And again, maybe I'm wrong. Maybe in this case, the value is something like that. Okay? But that's the idea, is I'm just going to take an average of the last, I'll call this sort of the last in average. So that last in average changes over time as we get more data and then leave off the old data, and we use that as our predictor. Now, as you can see, right, maybe we're wrong sometimes, so it's useful to think about how do we judge how good our algorithm is, how good our forecasting is doing. And basically, we're going to use a measure of how off were we. So if we had 5 data points here, and we try a moving average of the last 3 data points, then that would allow us to predict the last 2 data points using values from before it. And we can judge how close we were, how good we were, and use that as a measure of this model, a measure of this algorithm, how well it's doing. Okay? So we'll call these things the error in our prediction. Okay? And when we want to judge how good one of these models is, there's effectively 3 algorithms we can use, okay, to judge its accuracy. The first, and maybe the simplest, we'll call MAD, and it just stands for the mean absolute difference. So literally what we'll do is we'll sum up the absolute value of all the errors. Every time we made a prediction, how off were we? Take the absolute value of that, sum them all up, and then divide them by n, how many predictions we made. So in this case, we made 2 predictions. We would sum up the average, or the absolute value of the 2 errors, and divide it by 2, and say, on average, how off were we? Right? That's all it cares about. Now, the reason why we do absolute value, because we may, for one reason or another, let's say, predict a value, wrong color, predict a value too high, in which case, if we took the error, the difference between those, it might be negative as opposed to positive. So we take the absolute value here in our MAD calculation, simply so that we don't allow an overestimate and an underestimate to kind of cancel each other out, adding a positive and negative, taking the average of that to average out to 0 or something. So we want to know, on average, how off were we, whether we were over or under the target. Okay? So that's one measure of error of how good this model could be doing. Talk briefly about 2 more. The second is very much like it. We call it the mean absolute percent error. And the only real difference is when we've taken the absolute error, we divide it, okay, by the actual value. So we say, what fraction of the real value were we off? Were we 10% off? Were we 5% off? Were we 100% off? And then we take that divided by n to say, on average, mean, what percent off was our prediction? Again, we have to take absolute value. We don't want a positive and a negative error to cancel each other out. Okay? So that's MAD and MAPE, okay? 2 measures of error. The third and simplest one, I think, because it doesn't involve absolute error, is called the mean squared error, which just says take the sum of the square of all the errors and average that. So in this case, if I had 2 errors, I would square each one by multiplying it by itself, sum up those squared values, and divide it by n, how many of them there were. And that gives us a measure of error, okay? Doesn't involve absolute values, okay? But it does involve squaring, okay? And the squaring just ensures that whether the error was positive or negative, that we're always summing positive things. Because if you square any number, it's positive, unless it's imaginary. But we won't worry about that. So those are 3 ways we can judge how good a model is by how off it was. Okay? So let's look at some examples in Excel. So we'll compute moving average of some numbers here. So I'm going to put in some numbers. We can assume, say these numbers are sales numbers or something like that, of how much was sold. And we're wanting to create a moving average model that will predict the future, predict how much we think we'll sell in future weeks or future days or future years or whatever this is. So I'm just borrowing these values from the textbook. And that's what they are. Zoom in just a little bit. See those a little better. So let's say this is the week number, and these are the sales amounts. Okay. And let's say I wanted to compute a moving average model with 3 weeks. So after 3 weeks, I can compute the average and use that as my predictor for the following week. So let's say in week 4 is where I could compute the average that I've seen of weeks 1 through 3, okay? And that would be my prediction for week 4, okay? And similarly, so I've written this as the average of B2 to B4 in cell C5. I'm going to fill that formula down so that each formula is producing the average of the 3 weeks prior to it. Okay? So that's my moving average prediction for every week. And I can in fact use that to predict out into the future if I wanted to, by a week. Okay? Now moving average, obviously, can't possibly predict more than one time unit in the future if it relies on having actual values preceding it, right? You could theoretically predict 2 time units in the future by using your last prediction. You had to if you assume it was correct, and then the last, say, couple values that you've observed, you could use that to predict further in the future. But again, you're having to assume your prediction was perfect in that case, which is why the moving average model would be considered a short-term forecasting. It's only really good for predicting short-term into the future. The further out you want to predict, the more assumptions you have to make that you're being perfect about it. Okay? So here's my moving average model. And really what I want to ask is, if I'm going to predict a sale of 81 in week 11, next week out, how good do I think that might be? That is, how good of a model was I doing prior to that? If it was a very good model, then I can be very confident in this prediction. If it's not a good model, if it's very erroneous, then I probably shouldn't have very much confidence in its prediction. So let's see. If we were going to compute the error between my prediction and my sales, easiest thing is just take one minus the other, right? So what's the difference between what I predicted and what it really was in weeks 4 through 10? So if I take C5 minus CB5, that gives me an error. And I can fill that down and compute the error. So this is moving average model 3 error, okay, in column D. And from that, I could compute any one of my 3 metrics or 3 values or formulas. That's what I'm looking for. 3 formulas for overall error. Mean absolute difference, mean absolute percent error, or mean squared error. Okay? Just for example's sake, let's do all 3 so we can see how each one of them works. Okay? So let's start with the mean absolute difference. If we're going to compute mean absolute difference, the first thing we have to do is compute the absolute value of each error. So here I've computed the absolute value for each error. Label that using the function in Excel, just ABS, stands for absolute. Okay? And now I can compute MAD, mean absolute difference, as the sum of all the mean absolute errors divided by how many of them there were. Right? So in this case, there should be 7 of them. So what this says is, on average, I was 16.5 units off, according to the mean absolute difference. Okay? So on average, if you looked across these, I was about 16 units off each time, which means how much confidence should I have in this future prediction of 81 for week 11? I would assume it should be plus or minus about 16 of the real value. That is, I think I might be up to about 16 units off, since that's how off I was on average. Okay? So that's what we would use mean absolute deviation or mean absolute difference for, is to say how good of a model have we made, how much confidence should we have in its prediction of the future. All right, let's also do mean absolute percent error. So the easy way to do that, so we're going to take each absolute error and divide it by the actual value, the real sales value that we're trying to predict, to give us, in this case, a fraction. We can treat that as a percent, and then we're going to take the sum of those divided by 7, that's the number of them, and say, on average, so we format this as a percent, so on average, I'm 16 units off according to mean absolute difference. And according to mean absolute percent error, same basic thing, I'm using absolute errors, I'm about 19% off, about 20% off. So I may be over by 20% or under by 20% in some of these, okay? Which means, again, my prediction of 81 for week 11, I should expect that it's 81 plus or minus 20%. That's the amount of confidence I should have, roughly, in my future prediction, okay? Now, mean squared error, we'll compute it next. Mean squared error works a little bit different because we're going to square these values, okay? Sum up those squares, divide it by 7. So it's going to be a lot larger than either of these values because it involves squaring. And there's not really a sensible way you can make sense of it because, again, it's squared, okay? So we can't use it to say how off we are necessarily in our future prediction. So let's say error times itself, fill that down, and then compute the sum of all those squared errors divided by 7. So mean squared error is 391. And again, there's no real intuitive sense or no intuitive intrinsic value or units you can use for that. Okay? You can't say how off 81 is just by looking at mean squared error alone. In MAD and MAPE, mean absolute difference and mean absolute percent error, can kind of give you an idea of how off that is in terms of units or percentage. Okay? Mean squared error couldn't. Okay? Mean squared error has a value we'll learn later in the course why you would ever want that as opposed to these. But all three are effectively trying to tell us how good was this model, how confident should we be in its future predictions. Now let's imagine, same data, let's imagine we computed a new model, moving average model, but instead of using 3 weeks, 3-week moving average, let's use a 4-week moving average. And we can use its estimations of error to compare that to the moving average of 3-week model and say which model is better. Should we use more weeks or fewer weeks in our model? So let's do that real quick. So easy enough. Call this the moving average 4-week model. And each week is just going to be an average of the sales values of the 4 weeks preceding it. So we're only going to have predictions for week 5 through 10. And we can compute its error as the difference between our prediction and the sales number. We can compute its absolute error, the absolute value of that. Okay. Which allows us to compute the mean absolute difference as the sum of the absolute errors divided by the number of them. So in this case, there's only 6, not 7 predictions made. Print some of these. There. So here we can say, we can make some sort of estimation of whether or not a 3-week moving average or a 4-week moving average is better for this particular data set, judging them on the same sort of grounds as which one has the better mean absolute difference. Where better, of course, would mean lower. Right? We'd want a lower error on average. So a moving average of 3 weeks gives us a mean absolute difference of 16.5. A moving average of 4 weeks gives us a mean absolute difference of 17.3. So it seems, just looking at that a 3-week moving average would be better. We're off by a little bit less, albeit it's not a lot, but a little bit less if we use 3-week moving averages instead of 4. Now, Well, before I ask that, let's say what's the mean absolute percent error and mean squared error? Go ahead and compute those. So we can do mean absolute percent error by taking the absolute error divided by the sales number. Sum those divided by the number of them. And that would get us the percent value, one decimal place, say on average how much percent off are we. And then we can take every error and square it. Sum those and divide by their count. And tell us what the mean squared error would be. Now, in this case, as you would expect, all three measures of error, mean absolute difference, mean absolute percent error, mean squared error, all indicate the same thing, that a moving average of 3 weeks is better than a moving average of 4 for this particular data. So whether we're saying how off we are, what percent off we are, or whatever units you might imagine for squared errors, okay, all three of which suggest the lower amount of error is from the moving average of 3 weeks. Now the question might come, why would using less historical data be better? So using 3 weeks prior, why would that necessarily be better than using more historical data, like 4 weeks? So I'll ask you, do you have any ideas? Why in this case at least, moving average of 3 weeks is better than moving average of 4? Generally, you might expect more data, better model.
It's not very linear, right?
So the question, or the answer was it's not very linear. From which I think I know what you mean. Let's look and say, what do these values generally do over time? Are they increasing, decreasing, so on and so forth? So let's look. The easiest way we can do that, the easiest way to visualize, would be simply to just create a chart. So in Excel, I might just want to create a chart like that. So over time, what happens to these values, right? So in this case, it looks like initially value went up, and it went down, it went up a few times, it went down a few times, it went up, it went down, right? So the sales numbers in this data just kind of bounce up and down, more or less randomly, it seems, okay? Overall, it doesn't look like they're trending or going up. It doesn't look like they're generally going down. They just kind of go up and down, roughly between about, 65 and 112 or 13 or so, somewhere in that range, up and down, okay? So there's no necessarily good reason why a moving average of 3 or 4 would be better or worse. It's just whether or not you happen to see a peak or a valley in that sliding window of 3 or 4 weeks using to judge the next week, okay? No discernible pattern here, I would say. No particular reason. It's possible we might find a moving average of 5 weeks is better. So 3 is better than 4, but 5 is better than 4. Maybe 5 is better than 3, I don't know. You might go through that exercise yourself just to convince yourself that moving average might be better or worse depending on how many weeks or how many time units you choose. All right. Well, that takes us through a moving average model. Some data, a lot of data, will have a general trend that might look something like that, where overall the values seem to go up. Maybe not always, maybe it fluctuates a little bit, okay, like that. But overall, things are going up and up on average over time, okay? Moving average model in that kind of a case will always seem to underestimate because it's always using historical past data and averaging it. So the average of the past data is going to give a relatively lower value than the future if the future is always higher than the past. Does that make sense? So we might find other models that would help us account for something like that. Okay? To get us there, we're going to talk about 3 more forecasting models. Okay? The first of which is going to get us started. We're going to call the exponential smoothing model. Okay? And the exponential smoothing model, somewhat similar to the moving average, it's going to say, let's use some kind of average of the past to predict the future. The problem with moving average models is it says, I'll use, say, 3 values in the past to predict the future, and every 3 value is equally important. However, you might think the more recent past is more important than the far past. So you might want to say, use these 3 values to predict the 4th, but I probably should consider the 3rd value more important than the 2nd, and that more important than the 1st. That is, if there's a trend or if there's something happening with the data that's in a pattern, the recent past may be more indicative of the future than the distant past. So in that case, we may want to exponentially decay how important we think things are the further in the past it is. And here's the way we do that. So we're going to make our prediction, or our forecast, say for time t plus 1, as some value alpha times the last value we observed, we'll call that x, plus 1 minus alpha times the last prediction we made. Okay? So we're predicting the future as a weight between the recent past and the prediction we used for that. Where remember, this prediction, so if we write this out, alpha xt plus 1 minus alpha, we predicted the past as alpha t minus 1 plus 1 minus alpha prediction at t minus 1. Right? So we're predicting the future as alpha times xt plus 1 minus alpha times alpha xt minus 1 plus 1 minus alpha, or 1 minus alpha times 1 minus alpha prediction at t minus 1. Okay? And you could fill in that value and see that it would rely on xt minus 2, that is 2 time units in the past, and so forth. So our alpha value here, alpha is always going to be between 0 and 1. So you can see we're multiplying by some fraction the recent past, and then multiplying a fraction by a fraction, the past before it, and a fraction times a fraction times a fraction, the past before it, and so on and so forth. So the further in the past you are, the less weighting, the less importance we're going to assign to that by these fractions. We're going to give the most weight to the most recent past. Okay? So that's how exponential smoothing works. So this is our model here. And there is a parameter to this model, like there is moving average. We have to choose which value of n we want, like it is how many time units in the past we care about. Exponential smoothing cares about all the past. It just cares more about past, recent past than distant past. And the measure of that care that it gives is this parameter alpha. And we have to choose some value for alpha between 0 and 1. Okay? So this is our parameter versus this is our parameter in moving average models. So let's compute, say, an exponential smoothing model for this data, and we'll have to pick some alpha value. Okay? So let's do that. I'm going to get rid of our chart, and I'm going to go ahead and get rid of our 4-week moving average. We determined it wasn't any good anyway. And we're going to compute an exponential smoothing model, and we need an alpha value for that. Let's for now just pick 0.5, half. We'll see how that works. Okay? Now the exponential smoothing model, the one thing it requires is that you have an initial prediction. That is, we have to predict, we have to start somewhere, without much data, right? So let's assume we predict our first value perfectly, okay? And we won't measure our error for that, since we're kind of cheating. But we need that because if we're going to predict week 2, we're going to predict week 2 by multiplying alpha times the value we saw in week 1 plus 1 minus alpha times the value we predicted in week 1. Okay? So I'll let you see that formula there for a second. First I'll copy it, and then I'll let you see that formula. Okay? So again, every week, our prediction is going to be alpha, this value for alpha we've chosen, 0.5, times the last week's actual value, plus 1 minus alpha times the last week's prediction. Because last week's prediction was theoretically based on the week before it, and that prediction was based on the week before it. So you can see how every week we're making a new prediction, basing it on last week's observed value and last week's predicted value. Last week's observed and last week's predicted. And the amount we care about the observed versus the predicted is governed by alpha. Okay? So here's our exponential smoothing model. Let's compute error, absolute error, and squared error, and compare it. So again, I'm not going to compare week 1, since we don't really have any way to make a prediction for it. We just had to guess or had to cheat and look it up. So let's compute error, absolute error, and percent error. And then we can compute mean absolute error. We can compute, oops, that's not mean absolute error. This would be 9 values there. Percent error. And square error. Okay. So our exponential smoothing model, in this case, is off by about 19 points each week, 22%. Okay? Happens to be worse than our moving average of 3. But remember, we have this parameter here for which we can change the model, which would change its error. So you might think, well, what value of alpha should I use? Turns out, future weeks, maybe next week, might not get to it, so it may be the week after that, we'll talk about a way to optimally find the best alpha. Okay? We have tools to let us do that. For now, let's just use some guesses, and we'll just see if we can get the exponential smoothing model to be better than the moving average model. Okay? So let's try a higher value of alpha, which means we care more about the recent past than the distant past. So instead of 0.5, let's try 0.6. Actually, before I do that, I'm going to remind you of a little technique that we learned in week 1 called benchmark, or not benchmarking, no, we can call it that, base cases. So I'm going to copy the values I had, values only, for an alpha of 0.5, so I can use those as a comparison. So when I change alpha to 0.6, it's going to change all my numbers. But since I've copied values from when I had an alpha of 0.5, I have an easy way to judge those. So alpha of 0.6 seems worse than an alpha of 0.5. All of our errors have gone up, right? So we're getting worse. So maybe we should go back down. Let's try an alpha of 0.4. Got better. So an alpha of 0.4 is better than an alpha of 0.5. Still not as good as our moving average model. Maybe we should go down a little more. Try 0.3. A little better yet. Try 0.2. Now that got worse again. I don't know, let's try 0.28. I don't know. So you can see how now we have something that we can use, one specific value we can use to change how we make our predictions using the exponential smoothing model, for which we can actually start judging, okay, what would be a good value? How can we make this model better? That is, predict with less error. So in this case, I don't think I happened to find a value to make it better than moving average of 3. Perhaps you could. Okay? Perhaps you could. Any questions about exponential smoothing? No? All right then. If that's exponential smoothing, let's go one step further and talk about a model, exponential smoothing with a trend. Okay? So we're going to add another layer to this model to where we're not just predicting the future based on the past, but we're also trying to predict if there's a trend that the data is generally going up or generally going down, and use that to help aid our predictions. So we're going to predict not just exponentially decaying or smoothing the past, but also predicting a trend from the past, whether or not all of our predictions should be adjusted up or down based on an overall trend. Again, if we see data like that, that's generally going up, and a moving average model would do something like this. It would always sort of lag behind, underneath, because it never realizes that the future is always higher than the past. It just uses the past as the prediction. Exponential smoothing is going to have somewhat of a similar problem. Maybe not as bad in this case, because moving average averages all the past equally. Exponential smoothing may average the past with some decay and care more about recent than distant, and so it may come closer, but still will generally underestimate, underpredict, because it's not accounting for the fact that values are always higher in the future than in the past in general. Okay? So now we're going to add to our model something that will help it learn that kind of a trend and help it predict the future with better accuracy when there is that kind of a trend. Okay? So I want to make sure I write this down. Let me look it up. So our future prediction, forecast, for time t plus 1 is going to be the addition of two things. One is our exponentially smoothed value, we'll call that S, for time t, and the other is our trend, our current trend prediction for time t. Okay? So we need to compute ST and our trend t. Okay? ST is going to look similar to what the exponential smoothing algorithm looked like. We're just going to add alpha times the last value we saw and 1 minus alpha times the last prediction we saw. That's t minus 1. Okay? Actually, take that back. T minus 1 plus the last trend, because that's the last forecast we made. It was S plus T. So S is literally the same thing as exponential smoothing. T, on the other hand, we're going to use a new parameter called beta. And what beta is going to weight between is the difference between the last S and the S prior, and 1 minus beta times the previous trend. Okay? Sorry if that's getting kind of hard to read. So basically, we're exponential smoothing works the same. We're making a prediction each time based on weighting the last observed value and the last prediction we made. Except that our prediction also is broken into two components. that smooth value and this trend value. And the trend is just an exponentially smooth value of the difference between the last two predictions. That is, if the last prediction was higher than the prediction before it, we think the value is trending up. Or if the last value was less than the value before it, we think the values are trending down. And our trend will exponentially smooth over time. That is, we'll care more about a recent trend in ups or downs than previous trends. Okay? So let's do an example of this. I'm actually going to go ahead and just use a new sheet. We'll use a new data set. So let's say we had 14 values, something we can use. And let's just take a real simple case. Say we had 100, 100, 10, 120, 130, 140, 150, 60. We'll just do something simple where initially the values are the same, and then over time they just go up. Okay? Zoom that in. So this is our time, and this is our x at different time units. Okay? T and xt. So for our exponential smoothing, we need to compute two things. First, we're going to compute our smooth value, and second, we're going to compute our trend value. Okay? Now, should have left room for that, for this, but we also have two parameters that we're going to use to judge how this model works. One is alpha, which is what we use to govern how we decay or exponentially smooth our S value, our prediction, our raw prediction, and a beta value, which is how we exponentially smooth our estimation of the trend. Are we trending up or not? Okay. And again, both of those are just simply going to be exponentially smooth values with those that alpha and that beta. S is smoothing the X's. T is smoothing the difference between the last two S's. Okay, simple enough. So again, we're going to have to come up with a way to make an initial guess. Let's assume it's going to be perfect. Okay, so now we can say compute S for T2, that is time 2, as alpha times the previous X plus 1 minus alpha times the previous S. Okay. Use that to predict down and even into the future. Okay. T, on the other hand, okay, T, on the other hand, relies on the last two S values. So T, we can only start computing like S at time 2 as beta times, in this case we want S for time 2 minus S for time 1. And then we're going to add to that 1 minus beta times the previous T value. So again, we're going to have to come up with a way to initialize T. And the easiest way to initialize T is to say, let's assume there is no trend to start with. Makes sense. We don't have any history. We have no evidence of a trend. So our initial T is 0. Our initial S will just set equal to the X value. So we'll have to assume we see the first X before we can start making our predictions. So now we have a T value. Oh, I miscomputed that by not making the beta field an absolute guess. Can't do that. There we go. Okay. And from that, we can compute a forecast. So our forecast is always S plus T. think I made a mistake here. Can anybody see it? My S value is actually supposed to be the last x times the last forecast, which was S plus T. That's what my forecast is each time. Let me fix that. Okay, so now we can impute error as the difference between our forecast and the actual value. We can compute absolute error, the absolute values of each error. Compute percent error, error divided by the x value. And we can compute square error, error times itself. Percent, this is error squared. And from that we can compute MAD, MAPE, and MSE as the sum of either the absolute errors divided by their count. So here we have, what, 13 values, or the sum of percent errors divided by their count, or the sum of square errors divided by their count. Okay. So in this case, our exponentially smooth model with a trend could take this data, which isn't very exciting, just starts with the base value of 100, and then after week or time 3, starts increasing by 10 each time. And what you'll see is the S value, right, tends to lag behind, be too low for the value. But we've accounted for that by saying we're predicting that there's a trend that over time we figure out that values are generally going up by 10. So literally what you see here in the x's, every value goes up by 10. We've learned that fact after several time units and now have a trend value that pretty much equals 10, close to it each time. So we're predicting every time that the value is similar to the past plus 10 more. Similar to the past plus 10 more. Okay? Making our forecast relatively accurate, errors relatively low. So on average, we're off by 3.8 or 3% in this case. Now, we did have to choose values for alpha and beta, so we haven't talked about how you would choose those. Again, we'll learn later how you can optimize choosing those values and actually find the perfect values, or the best values for minimizing one of these error metrics. But for now, let's just talk about what these values mean. So alpha is how much do you care about recent past versus the history, past history. So this says the most recent value, we care as much about it, 0.5, as we care about the whole rest of the history before it. So we care a lot about one value in the past versus each individual value before it. A higher alpha means you care more about recent past than the history. Okay? So you might choose a high alpha if you had some intuition that says values in this X line here are changing over time, okay? And the way they changes over time. That is, it's not very useful to know how values were in the distant past. It's more useful to think about the recent past, okay? Beta, on the other hand, is telling you how much do I care about recently how the value changed versus in the past how values changed, how values trended, okay? In this case, okay, this is kind of a perfect scenario of there's a constant trend starting with week 3 and 4, I guess. So probably in a case like this, what you'll find is a higher value of beta is better because a higher value of beta says as soon as we see a difference week to week, we need to start caring about it here. That is, our t-value needs to go up quickly. Here it takes what? So starting with week 3 to week 4, we didn't predict that trend because we hadn't seen one yet. But then we noticed, hey, week 3 and 4, there was a difference here. For week 5, we need to trend that. We need to say we care about that difference, but we also care about past differences, right? So we only predicted a trend of 2.5 starting at week 5. Then we bumped it up to 5.6, then we bumped it up to 8. It took us literally 4 weeks before we started realizing, hey, the trend, it's 10, right? It's going up by 10 each time. Let's change the beta value to be higher, and these values should get to 10 quicker. Does that make sense? Because we'll care more about that trend faster. So let's see how that plays out. So again, I'm going to copy these two values, or these 3 values here. So we have a baseline to compare against. So this was beta of 0.5. Let's change that beta to be something like 0.9. Let's see how we do. So with a beta of 0.9, you'll see in week 5, we had a high trend. Week 6, we're almost predicting the trend perfectly. By week 7, 8, we've overshot it a little bit, but that's okay. We're still pretty close. We think the trend's somewhere in the 10 range, okay? Somewhere between the 9 to 12 range. And we eventually settle out in about the upper 9s, okay? You will notice that with a higher beta, since the trend is predictable, a higher beta predicts it quicker, leading to lower errors overall. Okay, so our MSE, all of those values went down from where it was with the lower beta because the trend was more constant, more predictable. Okay. So that's how you would choose alphas and betas. If you have intuitions for how values change over time or how trends might be getting changed over time, or if there is a trend or not, you would choose higher or lower alpha and beta values to reflect those intuitions. Okay. And again, later on, we'll figure out how to optimize those perfectly. Any questions? Okay. Well, before we move on to the last forecasting model, or the last forecasting algorithm, let's take a break. Okay. Before we take a break, though, let me make sure that you understand how this works and that you could, theoretically, given these x values, come up with models using moving average, exponential smoothing, and exponential smoothing with a trend predictions. Right? So you can figure out how to compute this f of t, or the s, t, and f, or the moving average values. Take the error, the difference between your prediction and the real value, and start computing things like these error metrics to say how good the model is. Okay. That's the key. Got to be able to do that. Okay. No questions, no problems. All right, let's take a break.